Chapter 1 Matter. In earlier classes, matter was introduced and discussed as composed of atoms or molecules and that it is found in the forms of solids, liquids and gases. In this class, the aim of the theme is to enable students to understand that these states are changed on the basis of interparticle state and interparticle collision. The kinetic theory of matter will be explained to explain the change of state. They will understand that in a physical and chemical change, the total mass before and after the change remains the same, which is known as the law of conservation of mass. Explanation of these theory and law would help students in understanding other behavior of the matter. Learning outcomes. After studying this chapter, students will be able to describe the main postulates of the kinetic theory of matter, explain the reasons of change of one state of the matter to another and vice versa on the basis of interparticle space and interparticle attraction and collision. Define and explain the law of conservation of mass using an example. Important terms and their definitions. Brownian motion. The zigzag movement of the small particles suspended in a liquid or gas is called Brownian motion. Diffusion. The spreading out and mixing of a substance with another substance due to the motion of its particles is called diffusion. Sublimation. The changing of a solid directly into vapors on heating and of vapors into solid on cooling is known as sublimation. Evaporation. The process of a liquid changing into vapor or gas even below its boiling point is called evaporation. Introduction. In our surroundings, we find many things and objects, living and non-living, for example, trees, water, animals, air, stars, etc. These things and objects differ in their properties, shape, size, color, smell, etc., but they are all composed of matter. In this universe, everything is made up of matter. Even human body is made of matter because human body has mass and volume which occupy space. The food we eat, the air we breathe, the matter we drink, the clothes we wear are all composed of matter. Definition of matter. Anything which occupies space and has mass is called matter. Here, mass is the amount of matter present in an object. The only conditions for something to be matter are that it should occupy space and have mass. In common language, matter is called material. Kinetic molecular theory of matter. The kinetic theory of gases, also known as kinetic molecular theory, is a law that explains the behavior of hypothetical ideal gas. According to this theory, gases are made up of tiny particles in random straight line motion. They move rapidly and continuously and make collisions with each other and the walls. This was the first theory to describe gas pressure in terms of collisions with the colors of the container rather than from static forces that push the molecules apart. Kinetic theory also explains how the different sizes of the particles in a gas can give them different individual speeds. Have you ever wondered why water boils faster at high altitudes? Or why inflatable poor toys seem flat after sitting in a cold garage? How about why you can smell a candle all throughout the house? All of these phenomena and many more can be explained by the kinetic theory of gases. Main postulates of kinetic molecular theory of matter. Kinetic theory makes many assumptions in order to explain the reasons gases act the way they do. According to kinetic theory, gases consist of particles in constant random motion. They continue in a straight line until they collide with something, usually each other or the walls of their container. Particles are point masses with no volume. Particles are so small compared to the space between them that we do not consider their size in ideal gases. No molecular forces are at work. This means that there is no attraction or repulsion between the particles. Gas pressure is due to the molecules colliding with the walls of the container. All of these collisions are perfectly elastic, meaning that there is no change in energy of either the particles or the wall upon collision. No energy is lost or gained from collisions. The time it takes to collide is negligible compared with the time between collisions. Kinetic energy of a gas is a measure of its Kelvin temperature. Individual gas molecules have different speeds, but the temperature and kinetic energy of the gas refer to the average of these speeds. The average kinetic energy of a gas particle is directly proportional to the temperature. An increase in temperature increases the speed in which the gas molecules move. All gases at a given temperature have the same average kinetic energy. Lighter gas molecules move faster than heavy molecules. Thermal energy. The temperature of a gas is actually a measure of its average kinetic energy, and kinetic energy of a particle is related to its velocity according to the following equation. Ke is equal to 1 by 2 mv square. 1.1, where Ke represents kinetic energy of a particle, m is mass and v2, and v square is the square of its velocity. As velocity increases, so does kinetic energy. Of course, the inverse is also true. That is, kinetic energy increases, so do velocity. You can see from this relationship how a molecule with a higher temperature will be moving faster. The temperature of the system is the average kinetic energy of its particles. Thermal energy is the total kinetic energy of all the particles in a system. Temperature, thermal energy, and the speed of a molecule are all directly related. Boyle's law states that for the pressure and volume of a gas, when one value increases and the other decreases, as long as temperature and number of moles remain constant, Boyle's law can be summarized by the following equation. PV is equal to K, 1.2, where P is the pressure of the molecules on the container, V is the volume of the container, and K a constant. The value of K always stays the same so that P and V vary appropriately. For example, if pressure increases, K must remain constant and thus volume will increase. This is consistent with the predictions of Boyle's law. Consider the box full of moving gas molecules, figure 1.1. The particles have the same energy temperature throughout. As the box gets smaller, they have a smaller distance to travel before they collide with the walls, and thus the time between collisions gets increasingly smaller. In a given amount of time, the particles hit the walls more, which results in a greater amount of pressure. The amount of moles is clearly constant as we are not adding or subtracting particles from the box. Another way of looking at this is that as the pressure increases, it drives the particles together. These compacted particles now occupy less volume. In order to compare a gas where either pressure or volume vary, we can combine the equations. P1V1 is equal to K and P2V2 is equal to K, because K is constant for both values of pressure and volume. P1V1 is equal to P2V2. Charles' law. Charles' law states that the values for temperature and volume of a gas are directly related. The equation for Charles' law is Vt is equal to K, where V is the volume of the container, T is the temperature of the system in Kelvin, and K a constant. For changes in volume and temperature, K remains the same. According to Charles' law, gases will expand when heated. The temperature of a gas is really a measure of the average kinetic energy of the particles. As the kinetic energy increases, the particles will move faster and want to make more collisions with the container. However, remember that in order for the law to apply, the pressure must remain constant. The only way to do this is by increasing the volume. This idea is illustrated by the comparing particles in a small and large boxes. Both particles leave at and return at the same time, but since the red ball travels a longer distance, it must be moving faster and have more energy. You can see that as the temperature and kinetic energy increase, so does the volume. Also note how the pressure remains constant. Both boxes experience the same number of collisions in a given amount of time. For Charles' law, combined equation can be written as V1 by T1 is equal to V2 by T2. The pressure law, or Gay-Lussac's law. The pressure law states that the values for temperature and pressure of a gas are directly related. As the temperature of a gas increases, so will the average speed and kinetic energy of the particles. This relationship is expressed in the following equation. P by T is equal to K, 1.6, where P is pressure of the particles on the container, T the temperature in Kelvin, and K is a constant. At constant volume, this results in more collisions and thereby greater pressure on the container. Because the value of K is the same for differing values of pressure and temperature, the pressure law can be written as follows. P1 by T1 is equal to P2 by T2, 1.7. Avogadro's law. Avogadro's law states that the volume of a gas is directly related to the number of moles of atoms contained in the gas. The equation for Avogadro's law is V by N is equal to K, 1.8, where V is the volume of the container, N the amount of gas as measured by the moles of atoms, and K a constant. Say a given amount of particles in a box. If you want to add more particles but you do not want to increase the pressure, you must make the container large. Diffusion. Diffusion is a simple process that can be explained by kinetic theory. When you open a bottle of perfume, it can very quickly be smelled on the other side of the room. This is because as the scent particles drift out of the bottle, gas molecules in the air collide with the particles and gradually distribute them throughout the air. Diffusion of a gas is the process where particles of one gas are spread throughout another gas by molecular motion. But not all gases diffuse at the same rate. Figure 1.3 above shows the perfume as being composed of all the same molecules. In reality, the perfume would be composed of many different types of molecules, some larger, more dense molecules and some smaller, lighter molecules. Thomas Graham, a Scottish chemist, discovered that lightweight gases diffuse at a much faster rate than heavy gases. Graham's law of diffusion shows the relationship between diffusion and molar mass. Rate of diffusion 1 by square root molar mass 1.9. Consider hydrogen and oxygen. The molar mass of hydrogen is about 1.0 grams per mole and the molar mass of oxygen is about 16 grams per mole. If you insert these values into the equation above, you get that the rate of diffusion for hydrogen is 1 and the rate of diffusion for oxygen is 1 by 4. This means that hydrogen will diffuse 4 times faster than oxygen. Effusion. Effusion is a similar process. Effusion is the process where gas molecules escape from an evacuated container through a small hole. It is assumed that while a molecule is existing, there are not collisions on that molecule. Note how the lighter molecules are the first to exit because they have a faster speed. As shown in figure 1.4, the smaller green molecules exit at a faster rate. This is where Graham's law of effusion comes in. It tells us the rate at which the molecules of a certain gas exit the container or effuse. See how Graham's law of effusion is derived from kinetic theory. Consider the equation for the kinetic energy of a gas ignoring rotation. K is equal to 1 by 2 mv square, 1.10. Because temperature is a measure of the average kinetic energy of a gas, two gases at the same temperature will also have the same kinetic energy. Thus 1 by 2 m1 v1 square is equal to 1 by 2 m2 v2 square. Simplify by multiplying both sides by 2. m1 v1 square is equal to m2 v2 square. By rearranging terms, we get v1 square by v2 square is equal to m2 by m1. Taking the square root of both sides gives the equation v1 by v2 is equal to square root m2 by m1. Where v1 is the average velocity of the molecules in gas 1, v2 is the average velocity of the molecules in gas 2, and m1 and m2 are the respective molar masses. According to Graham's law, the molecules that are moving around faster will effuse more quickly, and similarly molecules with smaller velocities effuse slower. Because this is true, we can substitute the rates of effusion into an equation below. This yields Graham's law of effusion. Rate 1 by rate 2 is equal to square root m2 by m1. This equation allows us to compare the rates of effusion for two different gases under the same conditions of temperature and pressure. It is important to note when solving problems for effusion, the gases must contain equal moles of atoms. You can still solve the equation if they are not in equal amounts, but you must account for this. For example, if gas A and gas B both diffuse in the same amount of time, but gas A contains 2 moles and gas B contains 1 mole, then the rate of effusion for gas A is twice as much. Root mean square RMS speed. We know how to determine the average kinetic energy of a gas, but how does this relate to the average speed of the particles? We know that in a gas, individual molecules have different speeds. Collisions between these molecules can change individual molecule speeds. This does not affect the overall average speed of the system. As we have seen demonstrated through effusion, lighter gas molecules will generally move faster than heavier gases at the same temperature. Real gases. Kinetic theory assumes that all gases behave ideally. However, we know that this is not the case. Obviously, real gas particles do occupy space and attract each other. These properties become apparent at low temperature or high pressures. Usually, the particles have enough kinetic energy that they whiz by each other without being affected by the push or pull of neighboring molecules. However, at low temperatures, the molecules have very little kinetic energy and move around much slower, so there is time for static forces to take hold. At very high pressure, the molecules of a gas become so tightly packed that their volume is significant compared to the overall volume. Also note that before a gas ever reaches absolute zero, it will condense to states of matter. Matter around us is found to exist in three different physical states: solid, liquid, and gas. Three different states of matter arise due to variation in the characteristics of the particles of matter. Matter is made of particles. Matter is made up of small particles. The particles of the matter are very small. We cannot see them even with a high power microscope. For example, a small drop contains about 10 to the power 21 particles of water in it. The particles of the matter have following characteristics. Matter is made up of small particles. The particles in the matter have spaces between them. This space is called intermolecular space. The particles in the matter are moving in nature because the particles of matter have kinetic energy. The motion of the particles increases with the increase in temperature. The particles in the matter attract each other, but this mutual force of attraction is effective only when the particles are very close to each other. In solids, the particles are closely packed and hence they have greater intermolecular forces, attractions, while in gases the particles are loosely held. Hence, they have weak forces of attractions. Change of state of the matter on the basis of interparticle space. Particles of matter have space between them. To show the spaces between the particles of matter can be shown by performing the following experiment by using water and sugar. It means that even after dissolving 50 grams of sugar in 100 ml of water, the volume has not increased. Here we can say by assuming that the particles of water have some spaces between them. When sugar is dissolved in water, its crystals separate into very fine particles. These particles of sugar go into the spaces between the various particles of water, due to which there is no change in the volume of water of dissolving sugar in it. On dissolving sugar in water, there is no change in volume. It shows that there are spaces between the particles of water. These spaces accommodate the sugar particles. From this, we also conclude that the particles of molecules in water are not tightly packed. They are somewhat loose, having spaces between them. Change of state of the matter on the basis of interparticle attraction and collision. The particles of matter have certain forces of attraction between them which keeps them together. This force of attraction, called cohesive force, depends upon the nature of the particles constituting that matter and the interparticle space, or in other words, the force of attraction or cohesion is different in the particles of different kinds of matter. This will be more clear from the following example. Take a piece of chalk, a small brick and an iron rod. Beat them separately with a hammer. You will observe that it is very easy to break the chalk into pieces, difficult to break the brick, and very difficult to break the iron rod into pieces. It clearly shows that the attractive forces between the particles of chalk are very weak as compared to that of brick and iron. Actually, these interparticle forces of attraction are maximum in solid state because the particles are very closely packed. These are less in liquid state and the least in gaseous state of matter. In another example, it can be easily proved by the fact that we can easily move our hand through air and water because the force of attraction between the particles of air, which is a gas, is very, very small. Likewise, because the force of attraction between the particles of water, which is a liquid, is also small, but we cannot glide past our hands through a piece of wood because the force of attraction between the particles of wood, which is a solid, is very strong. Law of conservation of mass. Imagine you enter a closed system. A room is perfectly sealed where nothing can enter the room and nothing can escape. In this closed system, you can light a candle and let it burn, watching as some of the wax seems to disappear as the flame travels down the wick. Where does the wax go? Is it truly disappearing? The law of conservation of mass states that in a closed system, the mass of the system cannot change over time. Look at the above example of the candle in the closed room. Though much of the wax itself is no longer present in its original form, all of the mass of the wax is still present in the room in a different form. When the flame was lit, oxygen gas from the room reacted with the candle wax to produce water vapor and carbon dioxide gas. If you mass the reactant oxygen and wax, it would equal to the mass of the products, water and carbon dioxide. You can remember the law of conservation of mass with this simple statement. The mass of the reactants must be equal to the mass of the products. Anything that has mass including matter and energy cannot be created or destroyed. That is, mass cannot simply appear out of nowhere and equally it cannot disappear. Matter may change forms, however, giving the illusion of nothing out of something or vice versa, but the mass of the matter is always the same before and after the change. If 22 grams of reactants go into a chemical reaction, then 22 grams of products must be produced. Importance of the law of conservation. Discovery of the law of conservation of mass helped to turn chemistry into the respectable science it is today. With the advent of the law of conservation of mass, chemists took the mystery and illusion of alchemy and brought predictability and reliability to the science of chemistry. The law of conservation of mass is very important to the study and production of chemical reactions. If scientists know the quantities and identities of reactants for a particular reaction, they can predict the amount of product that will be made. Chemical manufacturers can increase efficiency by applying the law of conservation of mass to their laboratory practices. Examples. Imagine you're lighting up your gas grill. The propane from your heavy gas tank reacts with the oxygen in the air, generating a hot blue flame. The products of this reaction are water vapor and carbon dioxide gas. Word equation: propane plus oxygen gas is water vapor plus carbon dioxide gas. Chemical equation: C3H8 plus 5O2 is 4H2O plus 3CO2. If you were to capture all of the water vapor and carbon dioxide produced as you grill your food, the total mass would equal that of the propane and oxygen that went into the reaction. If 100 gram of propane and oxygen are used, then 100 gram of water vapor and carbon dioxide are produced. In another scenario, you let a 10 gram ice cube melt within a closed container on a hot day. Though the ice cube will gradually change forms from liquid to vapor, the mass of the container will never change. Even once completely vaporized, the mass of the water in the system will be 10 gram. Fast track. Chapter at a glance. In this universe, everything is made up of matter. Anything that has mass and occupies space, that is, has volume, is called matter. Mass is the amount of matter present in an object. Kinetic molecular theory is a law that explains the behavior of a hypothetical ideal gas. Kinetic theory makes many assumptions in order to explain the reason gases act the way they do. The gas laws are all based on the properties of gases laid down in kinetic theory. Matter is made up of small particles. Particles in the matter have spaces between them. This space is called intermolecular space. The particles in the matter attract each other, but this mutual force of attraction is effective only when the particles are very close to each other. The forces of attraction between the particles are maximum in solids, intermediate in liquids, and minimum in gases. The law of conservation of mass states that in a closed system, the mass of the system cannot change.